I'm from the Institute of Photonic Sciences in Barcelona, Spain. Welcome today to another free physics lecture, which is our way of thanking the Aspen community for supporting the Center for 60 years. If you're not familiar with the history, informal summer workshops began here in 1962, while the winter conferences started in 1985 and are open to graduate students as well as senior scientists to spend an intensive week focused on a leading edge topic. The ambiance of these conferences is quite unique, as physicists can not only share their latest research in formal meetings, but also informally on the lifts, on cross-country trails, or on snowshoes. This week, other physicists and I are participating in a conference that was rescheduled from last March on many-body cavity quantum electrodynamics, or QED for short. This field aims at understanding and controlling the complex beauty of phenomena that can arise from interactions between light and materials in the quantum regime, and also using these effects in future technologies that exploit the laws of quantum physics. Today, we request that all participants in this event conduct themselves in a manner that is welcoming to all, treating each other with respect and consideration. Creating a supportive environment to enable scientific discourse is in fact central to the mission of the Aspen Center for Physics. You're highly welcome to ask questions at the end of the talk. And for that, please just use the raise hand function in Zoom, and I'll call on you. Tonight, we are fortunate to have Ana Asenjo-Garcia as our speaker. Ana is originally from Pamplona, Spain, and first became interested in physics in high school when she saw how physics could help to predict and model things that she saw in everyday life. From there, she earned her bachelor's, master's, and PhD degrees in physics from Universidad Complutense in Madrid. And fortunately for me, during her PhD, her advisor and entire research group moved to Barcelona, which is how I got to know her. Ana was then a postdoctoral fellow in my group for a year, and from there has had an amazing career trajectory that took her to Caltech as a postdoctoral fellow, and then to Columbia University, where she's now currently an assistant professor of physics. Ana already has earned a number of recognitions over her young career. Most recently, she was awarded a Packard Fellowship, which is given only to 20 of the most promising young researchers each year across all of the science and engineering fields. Aside from her scientific achievements, one thing that stands out about Ana, in my mind, is her passion to do science, share science, and talk about science, which you'll get to experience firsthand today. So without further delay, Ana, the floor is yours.
Thank you so much, David, for the extremely nice introduction. I really learned a lot from you doing the postdoc with you, so thanks for that as well. I would also like to extend my thank you time to the organizers of this amazing conference. It's my first conference since the pandemic, and it's something that I'm really enjoying. And well, I'm really excited to share with you basically the physics that has brought all of us together to Aspen, to this beautiful conference, and in particular, the science that I'm fascinated about. So today, if my clicker works, which it doesn't, let's see. Yeah. So today I'm going to talk about avalanches, which is perhaps a surprising thing, given that my talk is on quantum mechanics. Just, I'm not going to talk about the traditional avalanche where, we have a skier going down a mountain ridge and then, things happen to it. Oh, the video froze completely. But anyway, I guess you're somehow familiar with avalanches and they work like that. So I hope the guys survive. This sounds fun, but also extremely dangerous. So in the avalanches that I'm going to talk about, the scare is going to be a quantum fluctuation that triggers an avalanche of photons that are emitted by a collection of atoms into some collective, into a cavity mode. Okay, so maybe all these words do not mean that much to you right now, but I hope that by the end of the talk, they will. So I am interested in understanding emergent physics in complex phenomena. So what does that mean in particular? A complex system can be understood as a system that is more than just the sum of its parts. So imagine that we try to understand an avalanche just from the basic constituents like a snowflake. Like you can be as creative as you want. You will never predict such behavior. So this idea of emergence is a very powerful concept in physics because it occurs in many different physical phenomena. And also it also occurs in different types of systems like biological phenomena. So one example that I wanted to discuss briefly that is also related with photon emission is that of fireflies. So fireflies start seeing their neighbors and they start synchronizing as they emit light. So what I'm going to talk about today is another process of synchronization. That is what happens in an quantum optical system. So imagine that you have a bunch of atoms and they are going to start interacting with each other. As they interact with each other, they are going to synchronize and produce a very rapid burst of radiation, just like an avalanche of photons. So yeah, my clicker definitely doesn't work. Okay, I have to let go. Yeah, so to begin with discussing this physics, I want to start by just explaining, what's quantum optics. So quantum optics is basically the investigation of the interaction between light, and typically that light is laser light, is coherent light, not like the light that we receive from the sun, and matter. And matter for us is typically atoms or other types of quantum emitters that effectively behave like atoms. So quantum optics is interesting because it's quantum. So Richard Feynman famously said that nobody understands quantum physics. So I guess that even nowadays, that's perhaps painfully true. And also it has important applications, technological applications that I will discuss in the next slide. So one of the main questions in the field is how can we realize control atom-photon interactions such that we have, efficient and very controllable interactions between these basic constituents. So quantum mechanics has really revolutionized our world since its invention in the 20th century, and now it's it's the building block of one of many technologies. So example is computers. Other example, one that I have already mentioned is lasers. So basically sources of coherent light. If you go to the doctor, you may, whoa, that created a disaster. Okay, technical issue, no worries, will be fixed. Great. And I got a clicker, fantastic. Okay, so hopefully now it works. Yes, great. So if you go to the doctor, you may get a MRI scanner of your brain. Hopefully you don't, but things happen. So this is also based on quantum mechanics. And if you are interested in going to a place with precision, which we are, because we know, I personally use Google Maps, we may rely on GPS, and GPS synchronizes is synchronized thanks to atomic clocks. So basically systems of atoms are really good at timekeeping, and they form the most precise clocks that we are able to build. And this is just technologies that are currently, that we use in our everyday life. And there are, many surprises that may happen in, the future. And it's hard to stipulate what's going to happen, but, potential ideas are things like quantum computers or also different methods for cryptography. Okay, so let me start from, the most basic idea, that is, what is light? So light is basically an electromagnetic wave, as Maxwell told us in the 19th century. So he unified electricity with magnetism and explained to us what was electromagnetism. So light is a wave that propagates extremely fast at the speed of light. Nothing propagates faster than that. And basically it consists of oscillating electric field and oscillating magnetic field. And because of its wave-like nature, there is a periodicity to it that is determined especially by the wavelength. So light spans a very large range in energies or in wavelengths, but we can only detect a very narrow region. So that is what we call the visible region. And our eyes can detect light of these frequencies that is around 400 to 800 nanometer. So light, because it's a wave, it displays a very important property that is that of interference. So let me explain what this is. So imagine that you have an apple and another apple, then suddenly you have, when you add them up, you have two apples. That is not what happens with light. So imagine that you have two different waves and they are oscillating in phase. When you add them up, what you end up is with a wave that has double the amplitude due to constructive interference. Well, that's maybe perhaps not surprising. On the other hand, imagine that we have two waves and they are out of phase. So when you add them up, you have destructive interference and therefore there is no oscillation. So you went from two waves to basically a wave that has zero amplitude. Basically disappear if you want. So an example of this interference is that of what I'm going to show you here. So as a wave propagates and intersects a double slit, it will generate, each of these slits will become a source of electromagnetic field, and there will be interference between the two slits. And the important thing is that the electromagnetic field at any point in this plane is the sum of the generated by these two holes. Okay, so this is a superposition principle. And as you can see, there are regions where the amplitude of this field is large, and there are regions where you don't have any oscillation. So this is precisely this destructive interference. And so a similar concept of interference and superposition occurs in quantum mechanics. So let me just show you. Okay, sorry. Okay, another technical issue. It's good because then I get breaks. I can think, okay, what I'm gonna say. This is not done on purpose. Okay, so I wanted to show you what you should see if you look at this screen. Okay, so here. So as the light passes through the slits, as I said, there is a process of interference. And then in this screen, as I mentioned to you, there are points where you have very large amplitude, so maxima of the intensity, and points where you have minima, so very dark regions. Okay, so this is an interference pattern. And it's important that you notice that this occurs because you're adding amplitudes of the field, not intensities. Okay, and this, for instance, this interference pattern would never happen if you just have one slit. It's again a process of interference between the two slits. So, okay, so this is light, and then maybe are we done? And the reality is no, we're not done at all, because these three gentlemen came and said, wait a second, light is not a wave, it's actually a particle. So this is how the idea of photon came to be. So different experiments started to make people think that light comes as a quantum of energy. Okay, that's what a photon is. And de Broglie mentioned and realized that, well, actually we have a wave and particle duality. Light is a wave, and sometimes it behaves as a wave, but it's also a particle, a photon, and therefore sometimes it has this granular behavior of a particle. On the other hand, it goes the other way around. Electrons and atoms and matter and us are also waves. It's just that we are too macroscopic to, have a wave-like behavior. So then let's try to repeat the experiment that we did before of the double slit, but now with single photons. What should we see? If now we have single photons impinging this double slit, and we have our detector that is this black screen here. So let's do the experiment. So what you see is this granular kind of pattern. that as more and more photons start impinging on the screen, as time passes, it starts to resemble more and more the classical pattern that we had when we just thought that light behaved as a wave. So this is the beauty of quantum mechanics. So as the specific point where a photon is going to hit the screen is not known to us, it's random. And so, it will impinge the screen somewhere. But then as we repeat the experiment more and more and more and more times, then this behavior of, classical physics emerges. Okay, so the fact that light is, is quantum made people realize that, atomic energy levels are quantized. So if you look at here, you have a hydrogen lamp. So it's basically a gas of hydrogen that shines light with this purple color. And so if you look at the spectrum of light, what you will see is something like that. So let me compare it with this image here. So if you look at more or less the spectrum of the sun, you will see that there is a continuous frequency spectrum spanning from the purple to the red. And you don't see any discreteness to it. We receive photons basically for all frequencies. On the other hand, if we look at this hydrogen lamp, we can decompose this purple color into these very specific lines. So basically this emission pattern is a fingerprint for hydrogen, okay? So how can this happen? Well, this happens because of quantum mechanics. So basically the electron motion in the atom is quantized. And this is precisely what Bohr realized. So this is the Bohr model of the atom. We have a nucleus that holds protons and neutrons, and we have electrons orbiting around this nucleus. And this is, honestly, this model is not correct because there is no notion of trajectory in quantum mechanics. So we cannot have electrons orbiting like planets around the sun. But the thing that is correct in this model is that these orbits describe energy levels. So an electron that is in n = 1 orbit has a very specific energy, and 2 has also a very specific energy, and 3 and so on. So if the electron jumps from this outer shell to an inner shell, it has to do this in discrete steps. It cannot jump in between. So that's what explains this discrete emission, this fingerprint, because the structure of the atom determines the emission of the photon. Okay. So once you figure out that you understand the hydrogen atom, you understand how the electrons behave in the atom, how this gives rise to this fingerprint in the emission spectrum, then you can go down 2 routes. The first one is you may care about the behavior of the electrons. And then you may think, okay, let's understand materials. So these are collections of atoms. Atoms are very close, and the electrons are hopping between the atoms. So then this is what condensed matter physics is the physics of electrons and other excitations in solids. And it enables us to discover new materials like graphene, and also correlated and exotic physics like, for instance, superconductivity. If you care about photons, as we tend to do in this, in this conference, you may go down the road of quantum optics. That is the physics of, understanding photon behavior and light matter interaction. And this is how you end up discovering things like the laser, how you may generate exotic and quantum states of light. And also, you may care about how very discrete matter, basically atoms, interact with very discrete photons, which is, for instance, the photon that is held in a cavity between 2 mirrors. So this is basically the idea of cavity QED, and this is the basis of this conference. So this is what I'm going to be talking about. So let me explain to you more specifically how and why an atom decays. So an atom is a complicated creature, but we're going to understand it as a 2-level system. So this is an approximation that, let's say, works most of the time. So we have our 2-level atom. It has a ground state, and this is the lowest energy state, and it has an excited state. So if the electron of the atom is excited, which I will refer to as the atom is excited, we can look at the population in this excited state, and it is 1, okay? And then at some random time, what happens is that the atom emits a photon and it decays to the ground state. So this is a process called a spontaneous emission. So nothing effectively like that we can look at is telling the atom you have to release the photon now. That's why it's called spontaneous. And the photon is released into the environment. And the important thing is that the photons are emitted at random times. So imagine that we repeat this experiment. We place again our atom in the excited state, and boom, it decays. But now it's going to decay, emitting a photon at another random time. And we do it again, and boom, at another time. So then again, there is this granularity and randomness that we saw in the double slit experiment with single photons. So if now we average over all these times that we're repeating the same experiment, what we end up is with something smooth, that is an exponential decay at a rate that is called the spontaneous emission rate. And that rate is determined by the environment. And this is critical. So it means that how an atom decays is not just a property of the specific atom. Is it hydrogen? Is it rubidium? Is it sodium? No, it also depends on the environment. Is it in free space? Is it in close to a cavity, close to a mirror, close to a table? That's going to determine how fast it decays. So the question is how and why atoms decay, and they decay due to vacuum fluctuations. So we tend to think that vacuum is just a void, but it is not. The electromagnetic vacuum is far from being a void. There are fluctuations. It's like you have to think of like some noisy field, and these fluctuations produce the decay of the atom. They induce the atom to decay, okay, emitting a photon. And so, as I said, the atoms are going to be very sensitive to the environment. And so let me give you an example. So imagine that we place an atom close to a mirror. Depending on the distance to the mirror, the atom is going to decay very fast or very slow, okay? So you can play a game, and you say, well, now I'm gonna put 2 mirrors. Basically, this environment is what we call a cavity. And then depending on the cavity length, we're going to have an emission of photons that is enhanced compared to vacuum or suppressed, which means that we're going to be very efficient collecting the photon of the atom really fast, or we can have an excitation in an atom there forever. So depending on what we want, we may choose one thing or the other. So to control the emission of photons, we can change the environment, but also we can change the number of atoms. And this is because many atoms radiate differently, not just more. Again, this is a complex, many-body quantum system. And so you have to think that when these atoms are excited, they are going to start emitting photons, and these photons are going to interfere either constructively or destructively. So, it has some connection with the slit experiment. You can think of each of them as a quantum slit if you want. And now the behavior becomes collective and hopefully robust because you have many particles contributing to radiation. So, quantum systems are really complicated. And instead of trying to explain to you just from the get-go how many atoms, emit photons, I'm gonna try to explain it using something more classical, that is Firefly, which I already mentioned that, they undergo this sophisticated synchronization when they are together. So a Firefly uses bioluminescence to attract mates or prey. I am not a biologist, so really bioluminescence to me is just some chemical reaction, and the product of that is some other chemical output and some photon. Okay, so now we're going to do the typical spherical cow situation of a joke that we have a complex system, an atom, complicated because it's quantum. I'm going to approximate it to something that maybe I can, I can convey the physics to you more clearly, and that's a Firefly. Even though a Firefly is, it has many atoms, but it's also a macroscopic object, so it doesn't have any quantum behavior. So what happens if we have many Fireflies? Well, this phenomenon of synchronization is emergent. It cannot be explained from just understanding one. You can spend all your life understanding one Firefly, and you will not understand what is going to happen when you put many of them together. And this is because interactions are very important. So let me show you what happens. So I'm going to show you a video of an stimulated synchronization of fireflies. So I have to say not all species of fireflies synchronize, so only some of them do. I learned this yesterday, actually. That's very interesting. Anyway, so basically you have what you're going to do, or what we're going to do is we're going to stimulate this synchronization. This is a light, LED light, and it's gonna be radiating pulses. And so let's see if it works. So here it is. And then you'll see that, oh my God, it doesn't work. Okay, this is not great. How do we solve this? It's an unsolvable situation. It's like a video, a whole video, followed by another video. I can explain it, but it's not going to be as beautiful.
Bear with us for 1 second while we try to do this.
Okay.
I think you have to turn the camera on the physicist, and we all have to pretend to be Fireflies.
I see. This is now there should be a music like forgive us for the technical difficulties. No, it's working. I don't know how you made it.
Well, let's see if I can get it to work again with the Zoom running.
Oh, I see. If not, I will explain things, but it's gonna get intense because there are multiple videos. It does work. No. Okay, we can do it by steps. I will do everything now. Okay, so by steps. No, it doesn't matter. Let's see if it works. Okay, so I'm gonna explain. So we have this light, and this light, Firefly is close to this light, and so it's gonna synchronize with the light. And at the same time, all the other Fireflies are going to synchronize with the first Firefly and the light. And so what we should see is that they all start pulsating together. Hopefully this works. Yes, at least for 2 seconds. Okay, you got it, right? So, okay, good. So this is a situation where this synchronization, like every Firefly has its own internal clock that, makes it radiate every 8 seconds. But then because of this synchronization, there is no randomness anymore because there is a notion of order that emerges, okay, from these interactions. Okay, now the second video. That's gonna be a challenge. Okay, so now this is kind of a trick because we were tricking the Fireflies to be synchronized with this light, but we can also have a spontaneous synchronization. So hopefully this video will show it, and let's find out. Okay, wait, let me explain what this is before we get too ahead of ourselves. Okay, so this is something that I found while preparing this talk in the website of Dicke, which is a very talented artist. And so what she did is a simulation of Fireflies. Each of them again has its own internal clock, and they are firing randomly. At some point, I switch on a button that says nearest neighbor interaction. So the Firefly sees the neighbor and decides to synchronize with it, or basically it kind of accelerates its internal clock. So what we should see is that in the beginning, nothing very much happens, but eventually there is order that emerges from these interactions that are actually short range, and the order is long range. Let's see. Okay, so random, flicking, nothing exciting is happening at all. And then at some point I have, click the button, and then still nothing happens, but it should start soon. Okay, there you go, something that is more robust. Again, the nothing, boom, nothing, boom, nothing, boom. So you see, this is a spontaneous synchronization. And what happens again is, each Firefly has an internal clock. It interacts with its neighbor. It accelerates the internal clock. And these very small scale interactions give rise to this very large scale organization. And this is also a thing that also happens for atoms is that now is driven by quantum fluctuations instead of by, seeing the neighbor. So the question is just, how do atoms see each other? So fireflies have eyes, so they see that the other is, around. But my rendition of an atom has eyes, but of course, this is not realistic. So how do atoms see each other? They see each other again by vacuum fluctuations. So the same that they can feel that there is a mirror, they can feel that they have a neighbor. And therefore, they are going to interact with this neighbor via these vacuum fluctuations. And when they interact, they are going to become correlated in a quantum manner, which we call entangled. And of course, this is the case for just two atoms, but it may happen for multiple atoms. So for instance, depending on the type of the environment, we can have just two atoms like nearest neighbor correlated, or we may correlate all of them. So that's very interesting because it means that by changing the environment, we can change the atom-atom interactions, which means that we have control over the interactions between the atoms, and we can also design them, okay? So an example is that of a cavity. So again, we place now a bunch of atoms in between two mirrors. The fact that they are in between two mirrors means that they are coupled all together. So it's like an all-to-all interaction. And so that's a way of engineering interactions between the atoms. Another option is to have them in free space. Like for instance, here, you will need vacuum because if not, they're gonna be hit by molecules of air. But let's imagine that we have them here. And so in free space, the coupling between the atoms is different from the coupling between the atoms in a cavity. And this is because if you think of, imagine switching a flashlight in the night, as you may, you're familiar with this wave, as it propagates, the intensity decreases, okay? And this is a property that occurs because we live in three-dimensional space. So as a spherical wave spreads, then intensity decreases, which means also that in the case of the atoms, if they are close to each other, they are going to see each other. If they are far away, this interaction is going to decrease. So then now we have an additional degree of freedom or parameter that is the distance between them that we can control. And so I wanted to mention that this idea of controlling the environment was pointed out by Roy Glauber, who won the Nobel Prize for the theory of optical coherence. And he has a sentence that I really enjoyed when I read, that is that all the delicate and ingenious techniques of optics are actually exercises in the constructive use of noise, which is actually the constructive use of fluctuations. Okay, so here I'm coming to the point of the avalanche. We're going to have a bunch of atoms, so let's forget about the fireflies. We're gonna put them in between mirrors, and they are all going to be excited. So this is what is gonna happen. It's a process called Dicke superradiance. So they will start decaying, triggered by a vacuum fluctuation. So one of them will start. You don't know exactly which one because they do that in a superposition. And as they start decaying, they start synchronizing. And this synchronization leads to this rapid burst of photons. So you will have, if you plot the intensity versus time, you should see a very rapid race that corresponds to this very fast radiation, like a photon bomb. So this has been seen in experiments. And it's, now hopefully you can understand the idea of photon avalanche and how it's driven by a quantum fluctuation. So maybe the next time you are out there, you remember this other type of avalanche. So this is how Dicke superradiance look for a theorist. I just wanted to show you how things look for us. So we have a system where you have n atoms excited. And at the end of this photon avalanche, you end up with all the atoms being in the ground state. And as this process happens, you are lowering the number of excitations by emitting photons. And the states that you prepare are quantum states, which we denote by brackets. And these states are in a superposition, okay? So this is what gives rise to this coherence and to this radiation of photons. So this idea of Dicke superradiance is not just something that is cool and many-body and exotic. It's something that has, that enables new technology. So among the audience and in this conference, there are at least two authors of this paper. that use the idea of Dicke superradiance to create a new type of laser. And this new type of laser is robust to thermal fluctuations, which means that it can be used to improve optical clocks and to make more precise measurements. So this is an example of something that is very fundamental physics that, years later, Dicke superradiance was predicted to happen in 1954. This paper was published, correct me if I'm wrong, 2012? Yes. So, it took 60 years, 70 years, yeah. But, here is new technology coming from very fundamental science. Okay. So then the next question is, well, I'm a very curious person. And so I'm like, well, what if you get rid of the cavity? What if you now have atoms in free space? That's another environment. And can we have this type of correlated emission of photons? So again, in this case, instead of having this all-to-all coupling, the interaction is going to decrease with distance. And this is going to make the problem very hard to solve because this all-to-all coupling gave the problem symmetry. And physicists love symmetry because it enables us to solve problems. As we have this broken symmetry, this problem is extremely hard to solve. It's actually exponentially hard. So I'm just going to give you a flavor of what should happen. So if these atoms are very far away from each other, again, these interactions decay in free space, so they should not see each other. The interactions should be minimal, and we should have a boring, exponential decay with time in the intensity radiated. On the other hand, as they become very close, the interaction strength increases, and therefore we should get to the limit of Dicke superradiance, even though we don't have a cavity, even though we have a very different environment. So as I said, this is an exponentially hard problem. It's a many-body problem, so many atoms, many excitations, many photons. So what I can tell you is that, we tried. What we have found is that indeed, this is the case. There is a crossover, and this crossover between these two regimes depends on dimension, which is also something that typically happens in physics, where you have, for instance, processes like phase transitions that happen or not depending on the dimension of the problem. So then I want to not only explain to you what I'm currently excited about, but also what is the technology that enables a theorist to think in this way. So the first question is, all these ordered arrays that I'm talking about in free space, am I dreaming? Is this science fiction, or this is something that people in the lab can actually do? So the answer is that these things exist. So I wanted to show you images of atomic arrays that are created with optical tweezers. I'm going to explain in a minute what that is. I'm going to explain exactly what each of these pictures is. So here we have an array that is disorder of atoms. Every point here is an atom that is fluorescing. So basically it's emitting light, and somebody's taking a picture of it. So each of these points that are atoms are trapped with these optical tweezers that can be rearranged and form perfect ordered arrays. This can be done in one dimension, but it can be done in 2 dimensions as well. So, you can create the squares. If you're more romantic, you can create hearts. People are now becoming very creative. So this is a group in Chicago that decided that it was very nice to do create the Sears Tower with atoms. And this is a group in Paris that went beyond 2D and created a 3D reconstruction of the Eiffel Tower. I should say that these geometries, at least some of them, maybe like the 2-dimensional ones, can be also created with optical lattices. So basically beams of lasers that create this type of Eckart potential. So in this case, we have light that is being used not to drive interactions between atoms, but to trap the atoms. This is what an optical tweezer is. So again, it's one of these magic things of quantum optics where you have atoms and photons, and light can be used to mediate interactions, but can be used to trap atoms, can be used to cool them as well. So I wanted to mention Arthur Ashkin, who developed optical tweezers. And he won the Nobel Prize for them. He was 97, so I think he's the oldest Nobel Prize winner in physics. And when you win a Nobel Prize, apparently you get to do an interview very close to when you get the news, and they publish in the website the transcript. And so I really encourage you to read this transcript. It's fascinating, and there is a part of it that is really fun. So when he was developing optical tweezers, imagine how science fiction this is. This is it's 1969, and you're telling people that you can trap objects with light. So people thought that he was crazy, and he's recalling that it was a big surprise. And Asking was a pioneer, so he thought, well, instead of just trapping like piece of material, why not trap living creatures like cells, bacteria, viruses? And when he mentioned this to his colleagues, people said, don't exaggerate asking. I can tell you now that this is done routinely. So this guy was truly a pioneer. So how do optical tweezers work? So the idea is that you have a particle. That particle, again, can be a bacteria, can be some microsphere, can be an atom. And this particle is subject to gravity. So it's gonna fall. But when you shine light, you can imagine all the photons impinging in this particle. So as the particle tries to fall, the photons are stopping it. So this is radiation pressure. At the same time, we are focusing the light into a focal spot of a lens. And this produces a gradient force that confines the particle also in the transverse direction. So this is how you trap particles with light. So I wanted to show you a video of people trapping microspheres in water. So let's see if it works. Seems to work. No. Let's see, I can do it. Or not, who knows? Let's see. It's moving. Okay. Kind of. Well, I can tell you it's not as discretized as the video is showing. It's more continuous. But there you go. Okay, something like that. And then, you can move things around. So that's just the example that I wanted to give. So that's good enough. Don't worry. It's okay. I think the picture is there. So basically light, can drag objects around and can prepare atoms in order arrays. And so with this, I wanted to mention that these, experimental developments that have been happening in our community in the last 5 years have really opened the door to, theorist dreams on like, what can we do in these systems? So I wanted to mention some of the ideas that people are pursuing. So one example of emergent physics is that of a perfect mirror made of atoms. So if you have a 2D array of atoms and the spacing between the atoms is smaller than the wavelength of the light, as light impinges in this array, it can be perfectly reflected. So this is again because interference. And so this is not just a theorist's wild dream. This has been done in an experiment. So it's an experiment that happened in 2020, where people trap atoms in an optical lattice. They send light, and this is the reflectance that it raises to 60%. So still, it's an experiment, so it's still not 100%, but it's unbelievable to think that, if you think of a regular mirror, it's a very thick, metallic creature. Imagine that you could look to yourself in the mirror with just a mirror that is one atom thick. It's almost science fiction. People have used also arrays to implement protocols for quantum computing. So these are some examples. And also to realize more sensitive atomic clocks. Here you have, I don't know if you can see it, but this is a little array of atoms. And so basically, as we produce more sensitive atomic clocks, it means that we can measure more exciting things with more precision. And the last thing that I wanted to mention is that we can use arrays to do quantum simulation of materials. So for instance, arrays, as we can program the interactions, as I said before, between atoms, they may enable us to understand the physics of solids like magnetism or superconductivity. And a very exotic and exciting idea, whose proposer is also a part of this conference, is that you can do maybe something even more exotic than this. That is, you can use these programmable interactions between atoms to study emergent geometry and gravity. So I guess that I wanted to say that, this is just a path towards what I think is an exciting future. Our community has understood really well how to control single atoms in cavities. And as I said right 10 seconds ago, we have started to create light matter interfaces with a few atoms like this 2D mirror. But there are many open problems out there, like how to understand this many body complex quantum dynamics, how to do quantum simulation with these systems, how to measure better. Can we do a quantum computer using atoms and light? All these questions are out there. And what I think is exciting is that hopefully we will get, we'll get there. And so I'm sure we will find also other surprises. So with this, I'd like to thank, the people in my group. Stuart and Ricardo are attending the conference as well, and also my funding. And thank you all of you. And I'm welcoming any questions.
Thank you, Anna, for this wonderful talk. I see that we already have a question from Barbara. Barbara, do you want to unmute yourself and ask the question?
Hello, this is Barbara's husband, Michael. And
Hi, Michael.
I would like to ask, you spoke about vacuum fluctuations.
Yes.
My question has two parts, but the first part is, what is it that is fluctuating? And the second part is, what mechanism allows an excited atom to interact with the vacuum fluctuations?
Okay, so you have to think of the vacuum, the electromagnetic. So the electromagnetic field is a field, right? So it extends. And this field has, because it's a quantum field, it has what is called a 0-point energy. So there is basically, because of quantum mechanics, the vacuum has to have certain energy, which means that this vacuum can actually fluctuate, which means effectively, if you want to think about it, is creating photons that are, they are not true particles that will propagate out of nothing, but they live for tiny seconds, okay, or not seconds, like for very small times. So these quasi-particles are what under fluctuations, this creation. So the atom is now embedded in a bath of these quasi-particles, and this is a fluctuating force. So imagine that you have, it's the same as if you have a particle in a liquid. So as this particle is getting hit by molecules, and these molecules are creating a fluctuation in how it moves. So this is called Brownian motion. And they also create a drag, okay? So some friction, some dissipation. So this is exactly what the atom is experiencing. Is this fluctuation is making it decay, okay? So this is what produces, basically the atom sees this fluctuating environment and cannot help but, decay to its ground state. So this is something called, the fluctuation dissipation theorem. Whenever you have fluctuations or noise in a system, you also have to have decay. You have the two things are combined together. I don't know if that answers your question. It's a complicated question on the other hand. So this has been a debate for decades.
I think it does answer it. You're saying basically this is an electromagnetic phenomenon.
Yeah, for sure. Yes, it's totally. So basically the atoms, they decay because, or they can absorb photons because as light comes to them, okay, so when you populate the field, when the field is not in vacuum, you send, for instance, a single photon or a laser, they this produces a dipole moment in the atom. So it's an induced dipole moment. And so this induced dipole moment is the nature of it is electromagnetic. So it's, of course, electromagnetic behavior.
Thank you. Thank you. It was a very clear answer.
Okay, thanks.
Thanks for that great question. Is there anyone else who would like to raise their hands? Maybe while we're waiting, I can maybe ask a question that you can answer for the general public. Would you care to speculate or guess on what kind of exciting things might come out of our field in the next 10 years?
Wow, that's a hardcore question. Okay, so one thing that I didn't mention is that, I think there are multiple ways of answering this question. I can tell you what I find exciting, and I think also what what eventually the field will give rise to. One thing that I didn't mention is the same that for the same reasons that atoms can decay very fast, and you can prepare them in these states that radiate photons very fast, you can also prepare them in states where their excitation live together forever. So it means that you can store energy and information in these systems, and this information is going to live forever. Preparing that is extremely hard because precisely because this ensemble doesn't decay, it means that you cannot prepare from the outside these states that would live forever. So one of the things that I want to understand better is how, through these many body dynamics, you can reach to these states that are dark, that can be entangled, and that they can have also exotic properties for instance, measurement. Like, can you measure better with these states that also, they do not decay? If I'm being more ambitious, you could also say, well, can I decay into a cluster state so that I can do computation directly? I think that's not possible, but that's another possibility. And I think in general, this idea of control of and design of interactions is gonna enable new paradigms. So an example is this idea of studying gravity, which is it's wild and new, and who knows what will yield. And also, I think in our community for a while, people have been very focused, well, not so much maybe in the cavity QED community, but in maybe quantum science, condensed matter physics. People have studied a lot closed systems that are described by Hamiltonians. And I think with this idea of radiation and photons and so on, we are in this paradigm of open quantum systems. So it means that we get to do condensed matter again, but in another type of situation that will also enable things like new correlated physics, but also as the light is radiated from our system, we can measure it, which means we can act back on our system through some feedback, maybe make the dynamics controllable, and or at least characterize these many body dynamics. So that was a very long answer, probably hopefully understandable.
Thanks. I see we have a question from Scott. Would you like to unmute yourself?
Okay, can you hear me?
Yes. Hi, Scott.
Okay. Hey there.
Oh, I talk with a mask. Yes.
You spoke about a single atom width or thickness mirror.
Yeah.
Sort of a long-winded question here, but really what I'm after is would such a structure reflect a continuous any frequency, or
that's a great point.
Only discrete frequencies?
Well, it's not discrete. Your point is actually very important. So I lied a little bit when I said that we could look at ourselves in this atomic mirror and get a reflection. So this mirror is a very good mirror only in the region where atoms absorb light. So again, this is given by this spontaneous emission rate. So basically, an atom can only absorb photons within some frequency range. So light that is resonant to it and close to it. So these mirrors are very good mirrors only in this narrow frequency region. It doesn't mean that it's a discrete frequency. It's just a narrow region of frequencies. So if you imagine you have atoms that absorb light at 400 nanometers, if you send X-rays, the X-rays won't see the atoms won't see the X-rays. But if you send it at around 400 nanometers, it will be perfectly reflected.
All right, that's what I was wondering. I didn't know if you would get some sort of a different behavior of the structure than you would for the individual atom, which can only emit or absorb individual frequencies.
Yeah, well, it's a narrow frequency. It's never an individual discrete frequency. You have a little bit of wiggle room for a
Okay.
single atom and also for an array. The difference mostly comes from the fact that because of this interference process, if you have just a single atom and light impinges on it, the probability of absorbing this photon is very small because it's just a tiny atom. So the light, most of it will pass. But as because of this 2D array exists, there is destructive interference, and only there is constructive interference in the forward direction or in the backward direction. So eventually the forward directions get canceled for another reason, which is also interference. And eventually you get to, this system gets to reflect all the light. So it's, this collective behavior basically enhances the reflectivity of a single atom into something that reflects very strongly, but still within some narrow frequency band.
Thanks,
All right.
Scott.
Thank you. Yep, that's
Thanks,
fine.
Scott, for that great question. I see we also have a question from Connor. Can you unmute yourself?
Yeah, I kind of have a follow-up to that.
Okay.
Do you think a mirror like that, if you were to tune it so that it worked for infrared light, would have applications in like insulation, better insulation for homes and stuff, or is that just scientific applications?
I do not think it will have applications in insulation, mostly because you have to think of, well, I'm going to correct myself. Okay, so if you think of making this mirror with atoms, you have to place atoms in a vacuum. Okay, so your house is definitely not in vacuum. It means that if you try to trap atoms in an array, first you would need like enormous amount of power to just have the, the optical tweezers to create this 2D mirror. And then because of vacuum, any molecule of air will, destroy your mirror. So you cannot do that. The closest thing that you can think of is to do this physics is that part in particular, the part of the mirror. You can replicate it with classical systems. So you can do like arrays of antennas, and this is going to exhibit this macroscopic behavior of reflectance. So you could imagine of maybe, I don't know if insulation is the word, but you could imagine, if you care to do that, to build a bunch of metallic particles like antennas, and cover your house with that. And if you send light at the right frequencies, it will be reflected. I don't know why you would do that, but I can imagine also a lot of engineering challenges. But to be honest, this physics of interference, in particular for the 2D mirror, you don't need atoms. Like any type of polarizable object that responds to light would exhibit the same behavior if you have a collection of them and you place them right. So actually people build radars using the same type of ideas of interference with antennas. So not so much about isolation, but about detection and directional emission. Yeah. Thanks for your question.
Okay, so I don't see any other questions. So thank you everyone for your participation and your great questions. And also thanks, Anna, for the really illuminating talk and discussion.
Thanks, Eric, and thanks everyone for their questions. And thanks everyone for attending.
Finally, if you enjoyed today's public lecture, I would encourage you to join the email lists to receive news about future events. Please email Patty, P-A-T-T-Y, at aspenphys.org, and she can add you to the list. So thanks everyone for joining in, and thanks again, Anna.
Bye.